Algebra 2, Lesson 12-2, Matrix Multiplication. Now there are two types of matrix multiplication. We'll be going through both types in this lesson. One type of matrix multiplication is multiplying by a scalar. A scalar is a number that multiplies a matrix, which in other words means you just take a matrix and multiply it by a single number. Very simple to do, really easy, really straightforward. Scalar multiplication is multiplying a matrix by a scalar. The product of two matrices is another matrix. To find an element in the product of a matrix, you multiply the elements of the row from the first matrix by the corresponding elements of the column in the second matrix, and then add the products. That would be matrix multiplication. Matrix multiplication is much more confusing when you first start working with it than scalar multiplication is. Therefore, we're going to start with scalar multiplication because it's important, and then you'll understand how to apply that to matrix multiplication. All right. And most of the time when you use scalar multiplication, you're using scalar multiplication to resize a matrix, either making it bigger or smaller. Let's take a look at this. This would be scalar multiplication. If I had a matrix, let's say I have this matrix right here, 2, -3, 0, 6, and I wanted to multiply it by the scalar 3. All I'm going to do is take and multiply all of the elements of the original matrix by its corresponding parts. For example, let's see, I will multiply the 3 by the 2, and then the 3 by the -3, and then the 3 by the 0, and then 3 by the 6, just like I did in this middle matrix here, giving me the final matrix of 6, -9, 0, and 18. So to multiply a matrix by a scalar, multiply each element of the matrix by that scalar. For example, matrix A, A11, A12, A13, A21, A22, A23, I'm multiplied by CA. It's CA11, CA12, CA13, CA21, CA22, CA23. So not a complex computation. So let's say we're going to do this. We're going to find the sum of -3m plus 7n if m is 2, -3, 0, 6, and n is -5, -1, 2, 9. Now we can do this because we also have to add as well as multiply, and my two matrices are of equal sizes. Therefore, I can multiply them together. But first, I must scale them first before I can add them together. So let's do this. I'm going to take -3. I'm going to multiply it by 2, -3, 0, and 6. And I'm going to add 7 multiplied by -5, -1, 2, 9. So that's literally, that is what I am doing. So let's do that. If I multiply my corresponding elements, I'm going to have -6, +9, 0, -18. And I'm going to add that to that, -35, -7, 14, and 63. Now I'm just going to have to add my corresponding elements. If I add my corresponding elements, -6 and -35 is -41. 9 and -7 is 2. 0 and 14 is 14. And -18 and 63 is 45. All I did was multiply every element in each matrix by the scalar that they were asked to multiply by, and then I added my corresponding elements. -6 got added to -35, 9 got added to -7, 0 got added to 14, etc., etc. So we just multiplied by the scalar and then added the corresponding elements together to get our final matrix, which is right here. Now, there's also properties of scalar multiplication. Same types of properties that we have had before with other types of algebraic problems. Okay, you have the closure property, you have the associative property, which means order doesn't matter. When you multiply by a scalar, order doesn't matter. When you multiply a matrix by a matrix, order does matter. So this is only working for scalar multiplication. Make sure you're paying attention to that. So with scalar multiplication, the associative property applies, the distributive property applies, the multiplicative identity applies, and the multiplicative property of 0 also applies. The same properties as we've had with basic equations. Now, if you're going to solve a matrix equation with scalars, let's solve this following equation for y. We have negative 3y plus 2 times 6, 9, negative 12, 15 equals 27, negative 18, 30, and 6. Okay, so the first thing I have to do before I can even think of getting y all by itself is I have to multiply by the scalar. So I'm just going to simply do that. I have negative 3y equals, I multiply the scalar, 12 times 2 is 18, negative 12 times 24, and 15 times 2 is 30. So I have this, oops, it's not equal, it's plus. My bad there. It's negative 3y plus this matrix equals 27, negative 18, 30, and 6. So the next thing I need to do is I need to get so that 3y, negative 3y is all by itself. So I have to subtract this matrix. Okay, so if I'm going to subtract this matrix, negative 3y has got to equal the original first matrix, 27, negative 18, 30, and 6. And we're going to subtract from that 12, 18, negative 24, and 30. Now remember, when you're subtracting, you're adding the opposite. Okay, so negative 3y then will equal 27 minus 12, negative 18, minus 18, 30, minus negative 24, and 6 minus 30. So then negative 3y equals 27 minus 12 is 15. Negative 18 minus negative 18 minus 18, excuse me, is negative 36. 30 minus a negative 24 is 54. And 6 minus 30 is negative 24. So now I have negative 3y equals 15, negative 36, 54, negative 24. And you might say, but you haven't taught us how to divide. Don't worry about it. Dividing is the same as multiplying by the reciprocal. So I'm going to take this side of the equation and multiply it by negative 1/3, which means I'm not going to take this and multiply it by negative 1/3. So my scalar now is multiplying it by negative 1/3. Or in other words, dividing it by 3. 1/3 of 15, negative 1/3 of 15 is negative 5. Negative 1/3 of 36 is positive 12. Negative 1/3 of 54, or otherwise known as 54 divided by negative 3, is negative 18. And negative 24 divided by negative 3 is 8. So there you have y equals negative 5, 12, negative 8, and 8. And that's your final answer for solving that particular equation. So not all that complicated. And it doesn't matter what size it is. That was a 2 by 2. Let's look at this 2 by 3, 2 rows and 3 columns. Still going to do the same thing. Basically, you're going to set it up exactly the same way. Negative 3y is going to equal 10, 0, 8, negative 19, negative 18, 10. Now I need to subtract 7, 0, negative 1, 2, negative 3, 4. So if I subtract that, I should get negative 3y equals 10 minus 7 is 3, 0 minus 0 is 0, 8 minus a minus 1 is 9, negative 19 minus 2 is negative 21, negative 18 minus 3, minus a minus 3 is negative 15, and 10 minus 4 is 6. So I now have this, I have negative 3y equals 309, negative 21, negative 15, and 6. If I divide everything by negative 3, y will equal negative 1, 0, and negative 3. Negative 41 divided by negative 3 is positive 7, negative 15 divided by negative 3 is 5, and 6 divided by negative 3 is negative 2. And then we have our final answer. And I'm just going to highlight it because it's so much cooler. There's your final answer. So that is scalar multiplication and solving equations using scalars. Now let's take a look at matrix multiplication, which is a bit more complicated. The product of two matrices is a matrix. To find the element in the product matrix, you multiply the element of the row from the first matrix by the corresponding elements of the column of the second matrix, and then add the products. However, the products of two matrices, A and B, only exist if the number of columns of A is equal to the number of rows of B. Okay? Sometimes that's a little bit confusing, creates a little bit of confusion for people. The dimensions of a product matrix. If a matrix A is an M by N matrix, and matrix B is an N by P matrix, and the product matrix AB is an M by P matrix. Okay? For example, matrix A here has 3 rows and 2 columns. Matrix B here has 2 rows and 4 columns. This is a 3 by 2. Let's not have to do another highlighter. That doesn't look good. This is a 3 by 2 matrix. This is a 2 by 4 matrix. Okay? The middle number has to match. They have to have the same number. The number of columns in the first matrix has to equal the number of rows in the second matrix. If these are equal, then the matrices can be multiplied. And this, for 3 by 4, gives you your size of the matrix. In other words, when I multiply matrix A by matrix B, the size is going to be a 3 by 4 matrix. It's going to have 3 rows and 4 columns, and I'm done. We can multiply it because the number of columns in the first matrix equals the number of rows in the second matrix, and its final size is going to be a 3 by 4. So, and here they show you how to do matrix multiplication. You might be looking at A11, A12, and forgetting what that means. Remember, A11 means in matrix A, first row, first column, hence 11, first row, first column. A12 means first row, second column. A21, second row, first column. A22, second row, second column. So essentially, you're multiplying A11 to B11, and then A12 to B21. Your top row here gets multiplied by the column here, and then added together here. It's a little confusing when you first start it, but the more you do it, the better you get at it, and the faster or efficient you will become. So let's look at these 3 matrices, and let's see if we can multiply them. So let's find a product if it exists. So we have 12, 3, and 10, negative 5. First of all, let's see if it has, okay, this is a 1 row, 2 columns. And this is a 1 column, 2 rows. Okay? Oops. Let's get this right. Do it again. 1 row, 2 columns, have that right. 2 rows, 1 column. Now it's right. Those are the same. So my final product matrix is going to be a 1 by 1 matrix. Right? In other words, it's going to have 1 number when I'm done. Okay. So to multiply this matrix, everything in the first row has to be multiplied by everything in the first column. So simply put, 12 times 10 plus 3 times negative 5. 12 times 10 is 120, 3 times 5 is negative 15, so it's negative 5. There's my 1 by 1 matrix, and that is my final answer. Not too hard. Let's take a look at this one. Number 2 has 2 rows, 1 column, 2 rows, 2 columns. It doesn't match, does it? Not equal. Since it is not equal, no product matrix. Okay? Not equal, they do not have a product matrix, they can't be multiplied. All right, let's take a look at the third one over here. I know I'm going to need more space. I'm just going to math and later. This has 3 rows and 2 columns, and this and the second matrix here has 2 rows and 3 columns. So they match, and my final answer is going to be a 3 by 3. Okay, so I'm just going to go down and multiply away. And remember, first row by first column. Okay? So it's going to be 3 times negative 3 plus 2 times negative 2. And that goes in that first position. Then we go to the second method. Okay? The same first row, that column. Okay? And that's going to go in the middle because that's where it is. That's where its position is. This column, this column right here is in the middle column, so that's where that position is going to lie in. have to erase this really quickly because I didn't give myself enough space. So we'll do that again. 3 times negative 3 plus 2 times negative 2. And then we're going to go 3 times 3 plus 2 times 5. And then last but not least, we'll multiply that top row by the last column, which is 3 times negative 2 plus 2 times negative 1. I really didn't need a lot of space for that. Now we can see it. Okay. Now let's go with similar. So now we're going to go here and here. I'm trying to write a little bit smaller. So 4 times negative 3 plus 6 times negative 2. You'll notice these numbers stay the same. And if you set it up right, it's pretty easy once you've done the first column, the first row, I should say. Then we're going to do 4 times 3 plus 6 times 5. And then finally 4 times negative 2 plus 6 times negative 1. That's a little bit better space. And for the last one, we're going to be here. We're going to do it again. Here. Whoa! Let's undo that. I can't even read it. And we're going to do this. Just one in that one. There we go. So I can actually see it. All right. So then we're going to do 1 times negative 3 plus 1 times negative 2. In the middle column, it's going to be 1 times 3 plus 1 times 5. And in the last column, 1 times negative 2 times plus 1 times negative 1. Now we have to add those all together. Okay, so this would be negative 9 plus negative 4. Middle, 9 plus 10. Last, negative 6 plus 32. And my middle would be 4 times negative 3 is negative 12 plus negative 12. This one now, 12 plus 30. Last one here, negative 8 plus negative 6. And fine, last one, I'll leave the last one. Okay, so negative 1 times negative 3 is negative 3, and plus negative 2. And this one here, 3 plus 5, and finally this one here, negative 2 plus negative 1. Now we can actually add them together. So my final answer here, negative 13, 19, negative 8, negative 24, 42, negative 14, negative 5, 8, negative 3. And that is a 3 by 3 matrix. And that is the multiplication. I will tell you right now, you will have to multiply several matrices by hand. Eventually, I will show you how to do them on the calculator. I will never, ever ask you personally to multiply more than a 3 by 3 matrix because they get very hairy. I'm never going to make you have to multiply something super duper large by hand because it can be very complicated. However, I will ask you to multiply matrices of these sizes by hand without the use of a calculator, so you are going to have to learn your multiplication facts because I'm not even going to let you have a scientific calculator at your desk. So you're going to have to learn to multiply by hand and learn how to do this. I'm not going to show you how to use it on the calculator, so after I'm satisfied that you know how to do this by hand. If you want to Google it, go ahead and Google it. However, you have to be able to replicate this on a quiz and on a test without the use of a calculator, so you probably should learn how to do it properly. All right, now, notice that matrix multiplication is not commutative. Okay? We do have things like if you have matrix A, B, and C, the associative property works, the distributive property works, commutative property does not work. Okay? Regular multiplication is commutative. Matrix multiplication is not commutative. A times B is not the same as B times A. Okay? Matrix multiplication does apply the distributive property, and it does have the multiplication property of 0. So it has all of those properties, which are important. But you must realize it's not commutative, which makes sense, because if I had a matrix A, which was, let's say, a 2 by 3, and I have a matrix B, which we'll say is a 3 by 4, right? These would match, and your answer would be a 2 by 4. But if I try to do B times A, B is a 3 by 4, and A is a 2 by 3, you can't even multiply those together. This would have no multiplication, no matrix multiplication. So that proves that the commutative property does not work with matrix multiplication. All right, now let's apply it. You're like, oh goodness, aren't we done yet? Yeah, we're close. We're really close to being done. Okay. There are 3 ways to score in basketball games: 3-point field goals, 2-point field goals, and 1-point free throws. Yes, they are called field goals for those of you who do not know anything about basketball and think I'm talking about football. They actually call them field goals. In 1994, suppose a high school player scored 36 2-point field goals and 28 free throws. In 2006, suppose a high school player scored 7 2-point field goals, 21 2-point field goals, and 18 free throws. Using matrix multiplication, how many points did each player score? Okay, step 1. We have to figure out a matrix that will get the total count of types of scores for the 1994 and 2006 player. So let's just make a matrix. We're going to have the 1994 player be on the top row, and the 2006 player be on the bottom row. And we're just going to keep them in the same order: 3 points, 2 points, 1 point. Because that kind of makes sense. Okay? So we're going to do 3-pointers, 2-pointers, 1 point. That's the order we're going to put our matrix. Okay? So let's let X equal my types of scores. Okay, so in 1994, so you're looking at 1994 here, was 36 2-point field goals and 28 free throws, which means he scored no 3-point field goals. So if we're going to get his matrix, it would be 0, 36, 28. 0 3-pointers, 36 2-point goals, and 28 1. And in 2006, suppose a high school player was 7 3-pointers, 21 2-pointers, and 18 free throws. So he would be 7, 20, 18. So there's that matrix. There's B matrix X. So there's matrix X. And we've done matrix X. Create a matrix to represent point values for each type of score. Well, that's where the 3, 2, and 1 come in, because Y is going to be the point values. So the matrix Y is going to be, they are 3-pointers, 2-pointers, and 1-pointers. So that's the second. Step 3 says find the product. Okay, so to find the product, so we can multiply our 2 matrices together. So we're going to find the product of X times Y. Okay, if you remember, X was 0, 36, 28, and then 7, 21, 18. That was matrix X. And matrix Y was 3, 2, 1. So we have a 2 by 3 and a 3 by 1, so we can multiply those together. Okay. 3 by 3, 3 by 1, these match, so this is my final. And I get a 2 by 1 as my final size. Okay, so, doing that, I'm going to do matrix multiplication. This row by that column. Okay, so 0 times 3 plus 26 times 2 plus 28 times 1. And then my second row, 7 times 3 plus 21 times 2 plus 18 times 1. Multiply those together. We're going to have 0 plus 72 plus 28. Combine, you're going to get 21 plus 42 plus 18. And if I add all these together, let me extract these. I'm going to end up with 72 plus 28 is 100. And 21, 42, and 18 is 81. So my final answer then is In 1994, the player scored 100 points. And the 2006 player scored 81 points. And you might look at this and say, I could have solved this without a matrix. Yeah, sure you could, but we're learning how to solve with a matrix. Because eventually I'll show you how to calculate to solve it even faster than you could ever imagine, because the calculator can multiply matrices very, very quickly. I'm just not going to show you how to do it yet. If you want to learn how to do it earlier and want to Google it, that's fine, but you're still going to have to do it the old-fashioned way for me on your homework and in your quizzes and tests until I give you other notice. So we don't want to try to fudge that because it probably wouldn't be here. But that's basically